Anjan Rajapakse from the Department of Mechanical Engineering, University of Siriwardana. This is my final year individual research project, Hydrodynamics of Nanofluid based slug flow in Microchannel. Mankind is moving towards a smart, sustainable future with rapid improvements in smart devices. In that case, smart devices seek for more processing power. Consequently, increased processing power means more heat generation. Also, as the size of these devices are reducing, the area of heat removed is also reduced. This means more efficient heat removal is required. Microchannels are presented in these devices to achieve the desired heat removal. Since the microchannel heat exchangers are completely changing the world of cooling systems, we have developed a nanofluid-based slug flow in microchannel considering the higher bulk thermal conductivity of nanofluids. Slug flow is a mixture of two fluids in which large bubbles of secondary fluid are presented in the primary fluid. With the internal circulation in the mixture, it can remove more heat. Here we will use nanofluid as one of the fluids in the mixture. Although there is room for heat transfer enhancement with nanofluids in slug flow, there are several limitations like pump selection, system design, and flow stability. So, it is important to identify the best flow parameters for efficient and effective heat transfer. Here, we need to study the hydrodynamics of nanofluid-based slug flow very well. Let's look at my research findings. For an effective and efficient heat transfer, internal circulation is an important parameter. As shown in these figures, we have identified that both mineral oil droplets and nanoparticles provide higher internal circulations. As you can see in this figure, the axial pressure has increased within the slug area. It has not fluctuated as near the wall. A significant pressure variation can be seen in the front and rear points in the slug. Also, it can be seen that there will be a pressure drop increased when adding the nanoparticles. Generally, there exists a thin liquid film between the droplet and the channel wall. This has the potential to increase the heat transfer. Here, when adding the nanoparticles, we observe that this film thickness has decreased. So, when we analyze these results, we can see that although increased internal circulation and thermal conductivity has improved heat transfer performance, there are limiting factors such as increased pressure drop. So, it is very important to identify the better flow parameters for effective and efficient heat transfer.